Good evening, one and all. I welcome each and everyone present here to the first day of AICTE Training and Learning Blended Hybrid Faculty Development Program on concepts and applications of machine learning and deep learning for real world problems with hands on training using Python from 10th October to 21st October 2022, organized by Department of Electronics and Communication Engineering, College of Engineering, Perumal.
College of Engineering Perumal was founded in the year 2000 by the Cooperative Academy of Professional Education, which was established by the Government of Kerala. The college offers 4 undergraduate programs and MTech course affiliated to APJ Abdul Kalam Technology University and approved by All India Council for Technical Education.
The Department of Electronics and Communication, established in the year 2000, has 2 sanctioned batches for B.Tech in EC. The department is accredited by NB. The department has always been on a high growth path to keep pace with the ever increasing importance of the major disciplines of study and current technology trends. It is provided with good infrastructural facilities like well-equipped laboratories, library, well-qualified and experienced faculties, and technically sounded supporting staff, which help to mold engineering graduates of high caliber who excel in academics and industry.
AICTE Training and Learning. The Atal Academy was established on 24th September 2018 with the objective to plan and help in imparting quality technical education in the country and to assist technical institutions in advancing research, innovation and entrepreneurship through training. The Academy stressed upon empowering technical teachers and technicians using information and communication technology. The Academy provides a variety of opportunities for training and exchange of experiences such as workshops, orientation, learning communities, peer monitoring, and other FDPs.
This course aims at giving the faculties, irrespective of their trade, an insight into the basics and real-world applications of machine learning and deep learning. The sessions will be handled by experts from academic and technical streams. The course also covers case studies along with hands-on training using Python.
Course outline. Deep Learning Basic Concepts and Applications, National Education Policy 2020 Implementation, Case Studies, Early Detection of Surgical Cancer using Efficient Sender Detection, ML for Computer Vision, Research Methodology, Intent Values and Ethos, Classroom Conduct and Behavior, Deep Learning for Image Classification, Linear Algebra and Matrix Operation using Python, text summarization or translation using deep learning, speech and signal processing using deep learning, time and stress management, concepts of theoretical ML in signal processing, hands-on training of linear algebra and matrix operation using Python, hands-on training on text, summarization or translation using deep learning, hands-on training of speech and signal processing using Python, industrial with CDAC.
Once again, I welcome all of you to the training program. Now I welcome the organizing committee, convener and coordinator, Dr. V. Prasida Lakshmi Ma'am, our chairperson and principal, Dr. Bindu S.J., our resource person, Dr. Linu. Sorry for the inter. I welcome the resource person, Professor Dr. Linu Shine, and the course coordinators, Professor Pradeep T.S. and Professor Surjit S.
Now I welcome Dr. V. Prasida Lakshmi Ma'am for the presidential address.
Thank you. Respected Principal of College of Engineering Periman, Dr. Bindu, the resource persons of the sessions, all the faculty members who have registered for this FDP from various, who have attended this FDP from various engineering colleges, good evening. The Department of Electronics and Communication of College of Engineering Periman is organizing a faculty development program sponsored by AICTE from 10th October to 21st October 2022 in hybrid mode, which consists of 1 week online and 1 week offline. The online is from 10th October to 15th October and offline is from 17th October to 21st October. The objective of this FDP is value addition of teachers through applications of knowledge interest areas. It aims at imparting sound domain knowledge and associated skills to teachers, thereby empowering them. Let me congratulate Professor Surjit and Professor Pradeep TS for the course coordinator and the co-coordinator of this program for organizing this event. I would like to welcome all the participants and all the resource persons to this event. I hope this Atal FDP would enlighten the participants in the area of machine learning and deep learning, which would help them to promote learner-centered teaching. I wish all the success for this program. Thank you, all and all. Thank you.
Thank you, ma'am. Now I welcome our principal, Dr. Bindu S.J. ma'am, to give the inaugural address.
Okay. Good evening and warm welcome to each and everyone. I am extremely honored to have a chance of addressing you in this prestigious moment. It is indeed a happy moment for the EC department as well as College of Engineering, Periman. Once again, I am happy to announce you that today the EEE department is also organizing this Atal FDP in hybrid mode. I would like to take this opportunity to congratulate the convener, Professor Prasida Lishmi, and the course coordinator, Professor Pradeep and Professor Surjit, for realizing our vision beyond our expectation. So we all know that the machine learning has become one of the most exciting technologies of our time. This exciting field opens the way to new possibilities to our daily lives. Deep learning has gradually become the most widely used computational approach in the field of machine learning. Nowadays, it is considered as the core technology of today's fourth industrial revolution. Due to its learning capabilities of this one, it is widely applied in various applications area like healthcare, visual recognition, cybersecurity, and many more. I take this opportunity to congratulate each one of the participants for attending this FDP. Keep on refresh ourselves by attending this FDP's conference workshop so that we can impart quality education to future generation. So next generation must be at least one step ahead of us. So hereby I declare that the FDP on the computational technology and machines learning and deep learning with the Python hands-on training is inaugurated. I wish all the participants grand success of this all the coming days, and the organizers have grand success for successfully completing this FDP. I wish all the success too, and thank you.
Thank you, ma'am. Now, without further delay, let us start our first section, Deep Learning Basic Concepts and Applications. To take this section, I welcome a resource person, Dr. Linu Shine, Ma'am, Assistant Professor, Rajiv Gandhi Institute of Technology. She started her career in 2005 as lecturer in Department of Technical Education, Government of Kerala, and is currently working as assistant professor. Dr. Linu Shine ma'am has completed her BTech in electronics from Model Engineering College, Kollam, Model Engineering College, and owns a PhD in computer vision. She has done research in various fields and owns more than 10 publications and articles. It's my pleasure to extend a cheerful welcome to you, ma'am.
Hello. Thank you for the warm welcome. Am I audible now?
Yes, ma'am, you're audible.
Okay. Hope the screen is visible.
Yes, ma'am.
Okay. Today we were talking on our discussion. Our discussion is on deep learning, and here we will discuss the basic concepts of deep learning and its applications. Now, moving on, the quest for making uh, an artificial systems were there from the time immemorial, and this quest gained a momentum when or it gained widespread attention in 1997 when the Deep Blue of IBM defeated the reigning champion Gary Kasparov in chess. But the chess was just a 64 columns and only 32 pieces. And here the moves are well defined. So when a well defined computer program can win a game like this. And later on, with the further advancement, there came in 2015 another champion called. We have another success story that was attached to this artificial intelligence. That was when this Lee Sedol, an 18 times champion in AlphaGo, was defeated by Google's DeepMind computer. And this Go game was much more difficult and it needs much more strategic plan when compared to our chess. And the advancement or the gain or success of deep learning does not limit on this games based applications. It has immense application, as you know, in the case of driverless car. Like we have seen Google's Waymo driverless car and Tesla's driverless car, etc. That is gaining more and more momentum on roads now. And there are applications like automatic handwriting generation and recognition. And with nowadays, we can restore our old images or old pictures that was taken long back, and we can there is a provision of colorizing the black and white images, and the colorization of black and white videos also available is now here. And there is a technology called deep dreaming where you can generate artificial images from existing images. And with this advancement of this deep learning or the application of deep learning in our medical sciences, we can detect the growth delays in children, and it can also predict the demographic growth. And also, we can add our sound to silent films, and it can also create automatic. There is news generation is also available, and one common application that we are familiar is the automatic translation from any language to any other language. For example, our Google Translate. Now, what exactly is our deep learning? Deep learning is a class of machine learning algorithm that uses neural network, which contains a hierarchical of layers that extract these features automatically from the data and then make predictive guesses on the new step data. Now, what is then machine learning? So this machine learning comes under the broad spectrum of artificial intelligence. And artificial intelligence is any program that we are trying to imitate human or mammalian behavior. And under this, there's a subset called machine learning that allows the system to learn automatically and improve from experience. And here the difference is we need to identify the features of a particular problem and based on these features we are developing an algorithm, and from this it will develop a model to recognize the corresponding task, or to realize a corresponding task. And our machine learning is further a subset of deep learning. And when we compare it with our machine learning, the deep learning advantages is here also we are trying to automatically learn from the data, but there is no need for extracting the features by any humans. And here, these features are automatically learned by the system itself by using a set of hierarchical layers called neural networks. And why do we need this deep learning? And the advantages here are it works with unstructured data and it can solve complex problems. And there is we can have an automatic feature extraction unless when compared with our machine learning. In machine learning, we need a human should explain or extract features relevant for a particular problem, and based on that feature only we will get the result. But in this case of deep learning, the relevant features are automatically extracted from the by the network, and based on this we will get our output. And when compared to all other algorithms, our deep learning has best performance. Now, the role we have taught a term called neural network, and all this is deep learning or machine learning is loosely connected to our human brain. It is trying to mimic the human intelligence system or brain system. So, in human brain, the basic fundamental unit is a neuron. It consists of dendrites, a cell body, and consists of nucleus and an axon and an axon terminals. And here, the dendrites are in input terminals where it gets activation from another set of neurons, and at cell body it will define whether the next set of neurons should be activated based upon the thresholding function. And this, once if the neighboring cell need to be activated, this signal will be passed along the axon and passed to the next cell using the axon terminals. So, and this neural network uses a similar kind of structure. We cannot say it is exactly similar to a mammalian neuron, but it uses some properties of our neural network. Sorry, neurons. And our neural network is a similar kind of structure like a mammalian brain. It consists of interconnected neurons that takes input or receives input and process it in the different layers to produce the output. So the general structure is shown here. We have a number of inputs, say x1, x2, etc. up to xn, and each input is taken according to its weights. That means how much weight should be given to a particular input. That is decided by these weight factors W1, W2, whether a particular input should be given a higher weight compared to other, etc. That is denoted by this weight W1, etc. up to Wn. So each input has an associated weight, and all these weights are summed up at the neuron cell body, and to each cell we will add a bias term, and based on the output, based on activation function, we will have a output. So the basic structure is a perceptron. This perceptron is a can be a single neural network, or it consists of more than one neural network. So in its basic essence, it can be made up of a single neuron. Here the structure is same. We have a set of neurons. We have set of inputs, say x1, x2, etc., xn, and each neuron or each input is associated with a set of weights w1, w2, etc., wn, and each we will take a weighted sum of each of these inputs, and it is passed through an activation function that decide whether the next set of neurons should be activated or whether the corresponding output is enabled. And we will check with our required output, and if there is an error, that error is fed back, and based on that error we will adjust the weights until we will get the correct matching output. So the process is during the training process, what happens here is we are trying to reduce the error between the predicted output and the actual output. And during this training process, what happens here is this weights W1, W2, Wn get adjusted in such a way that our error is minimum, and based upon the input, we will have a correct mapping to the output. So this is the fundamental unit in all type of neural network. Now let us see how an AND gate can be implemented using a perceptron. For example, our inputs are A and B. We know that there are 4 different combinations for AND gate. One is 0, 0, 0, 1, 1, 0, and 1, 1. And an AND gate will have output 1 only when our input conditions is 1, 1. In all other cases, our output is 0. So here what we do is we will select a thresholding function such that whenever our weighted sum is equal to or greater than 1, our output is 1, else our output will be 0. So during the training process, what we're trying to do is we will find out a correct weight. Here, what weights should be given to this W1 and W2 to get our correct output. In our correct output cases, our input A equal to 1, for input A equal to 1 and B equal to 1, our output should be 1. So at one particular iteration, we got the answers to be correct, and the weights we have selected as 0.7 and 0.7. Now let us see. When we take the weighted sum, when we take 0.7 into 0 plus 0.7 into 0, the answer is 0, and it is obviously less than 1. Similarly here, it is 0.7 multiplied by when A is 0, when A is 0 and B is 1, this will be 0.7 multiplied by 0, and this is 0.7 multiplied by 1. Total sum is 0.7, but the value is obviously less than 0. So the output is 0. Now here again your sum is 0.7. This is 1 and this is 0. So your total sum is 0.7. The answer is again less than 1. So your output will be 0. Now when both are 1s, the total sum will be 0.7 into 1 plus 0.7 into 1. The total value will be, sum will be 1.4, and the result is greater than 1. That means our output is greater than 1 means the activation function or the thresholding function we have used is theta equal to 1 or greater than 1. So our output is 1 only at this instance, or in all other cases our output will be 0. So now we can come back to the different uses. One is we mainly use deep learning for here is our computer vision. So in the case of humans or any animals, we can see the surroundings and perceive many or understand many things and origin the data what we are seeing in front of us. That you can recognize a friend, or you can identify what is going on in front of you, whether a person is running or crying, etc. So our aim is to create an artificial system that can process this visual data and perceive this data and reason about this visual data, and take the actions or recommendation based on this information. This visual data can be anything, like it can be images, or it can be videos, or a medical data. to be in the case of images, you need to check whether it is an image of some dog or a cat, or is it a image of flower, etc. Or it can be in case of videos, we can check whether some anomalies are there, or in the case of medical data, we can check whether tumors or some kind of malignancies are there in the data. And in this way, we are providing some expert systems. And why this is important here is everywhere we can see the world is dominated by cameras. Even in your mobile phones, you have one or two cameras inbuilt with them. And what these people are doing is they are taking pictures, videos, and uploading them into social platform. So there are millions of hours of data are getting uploaded to this social platform. So it is humanly impossible to analyze all these videos by a single human or a set of humans. So we need artificial systems to analyze these data and take appropriate actions. Now, again coming to the topic, we have heard a term called learning. In the deep learning, there's a term called learning, and here learning means uh, it is the attaining. It means the means of attaining the ability to perform a particular task. And here we need to. Our aim is to build artificial systems that can learn from our data and experience. So we have said we need to have an ability to learn from some learn from experience, and here we need to learn. Learning means our ability or our machine should have some ability to perform the task. And what are the different tasks here in in the field of computer vision? One is classification. It can be a regression, transcription, machine translation. Classification means you're trying to assign a label. For in the case of vision or images, you're trying to assign a label for every image. Regression, for example, if you need, instead of giving a label, you need to predict what is the exact value. For example, based on the past rainfall levels, we need to check whether it will be raining today or tomorrow, or what is the stock price after 2 weeks for a particular brand. So in those cases, we need a regression. Transcription, here we need to convert some unstructured data into some structured data. For example, your automatic number plate recognition. That is an example of transcription. Or converting a voice message into text message. So here again, we are converting an unstructured data into structured data. Machine translation, as you always know, it is an example is our Google Translate, translating from one language to another language. Maybe translating from German to some English or something like that. And there are anomaly detection to detect some outliers like tumors or some traffic anomalies, etc. And synthesis and sampling, the list still goes on. You can add any number of items to this task. And now coming to our topic, our image classification. And in image classification, but then now what does the term classification means? Here, we need to make a learning algorithm that produce a function mapping. See, our input is X. Our algorithm should map our function to set of labels, say 1 to K. So we need to find which of these K categories will our input belongs to. That means our model, during this training process, we create a model, and our model needs to assign an input described by a vector, say X, to a particular category identified by the numeric code Y. Now, you can classify different data like vectors, some features, etc. Here, we are dealing with image classification. Now, what do you mean by image classification? As we have said earlier, it is assigning a label to a particular image. For example, here you can see a set of images, and the first image we call the name apple, second one rose, car, a ship, cat, a horse. So, what exactly are we doing here? Here it is just a two-dimensional image, but for this 2D image, what we are trying to do is we are trying to give a label or just a single name. And this single name we call as a label. So in image classification, our function is we have a two-dimensional image and our aim is to map this two-dimensional image to a particular label. So this image classification is a core task in computer vision. For example, here you can see an image of cat, and here our task is to assign one particular label for this image from a set of labels. Say your label set can be dog, car, truck, plane, etc. One important point to be noted here is for image classification job, the system should know ahead how many number of classes you are going to show or how many different kind of images are there in your total system. So once your system is learned, your system can recognize only these set of images. If you're taking an image out of this box or out of this set of images, even if your algorithm is trained, uh, even if your algorithm is trained and working perfectly for that particular set of data, this algorithm cannot detect what is a new image given. For example, here you have, let us assume we have only four set of classes: dog, car, truck, and plane, and your algorithm can neatly detect, it can correctly detect an image of dog, car, truck, and plane. Can correctly differentiate. And if I try to give an image of rose, in which the algorithm was never trained, it will not detect. It will give or throw out a label any of these four labels. A rose can be labeled as a car or a truck or a plane. It has equal probabilities. So the image classification algorithm just spit out a name that is given during the training part. So for a human, this image you can easily recognize. Even a child can recognize this is an image of cat. But for a computer, this is not as much easy. This computer will not get this holistic picture of an image of a cat from this holistic picture of a cat from this image. For a computer, it sees as a gigantic grid of numbers. For example, let us assume this image has a size of 800 by 600 height and width, and there are three color channels RGB. Then it is a gigantic grid of size or of matrix of size 800 by 600 by 3, in which the numbers ranges from 0 to 255. So it is for a system, it is just every image is a set of numbers, a grid of numbers. And the output of a trained image classification algorithm will be like this. This image can be 82% can be a car, or 15% a dog, 2% cat, or 1% monk. So, sorry, this is the connection. It can be 82% cat. And for a human, if I give an image like this to a child, it says that it's an image of cat. It doesn't have, it will not associate any probability. The child will not associate any probability. It definitely, it's just a cat, image of a cat. But such kind of prediction is not possible with our computer-based algorithms. Now, there are many challenges with this thing. One is the viewpoint variation. For example, if I take the picture of the cat from a different orientation, what happens here is the values in this gigantic grid or the matrix values will be getting changes when the camera moves. That means these are the different images of the same cat. But when I see the corresponding pixel values, all the pixel values are extremely different from the neighboring image. So for a computer, it is difficult to identify all these pictures refer to same label cat. But for a human, we can easily identify all these images refers to cat itself. So this viewpoint variation very much affect the working of a making of an intelligent algorithm for classification. Next one is illumination variation. We can see that the only difference here is between these two images are the lighting is different. But when for a grayscale images, the values are changing drastically when the illumination changes are different. For a grayscale image, each value corresponds to the intensity at that point. So here, the intensity values get changed when the illumination changes. This cannot be recognized by a normal system. So this is another challenge offered in the computer-based system. Now, for us, we can see that these two are the images of a human. But when we have this much scale variation, this is again difficult for a computer to recognize is as a human with the computer. Now, we can see here different images of the cat in deformed. It's a cat, one cute animal that can be appear in different shapes. So, for a human, it is quite easy to identify all these images contain cat. But for a computer, the pixel values again changes, and it is really difficult to perceive what is content of this image. Now, another bigger challenge is occlusion. Even if a smaller portion of the cat is visible, here you can see a cat under the blanket, here a cat hidden under bushes, and it just a cat peeping out. And the fourth image, you can see just the tail of the cat. Still, you can identify there's a cat under that pouch. So, in all these cases, the pixel values is completely different in each figures, but the content is almost same. It all contains cat, and this is again a challenge for an image recognition or image classification algorithm. Now, another great challenge is background clutter. When the image or when the object smoothly blends with the background, again there is no pixel variation between. There is not much pixel variation between the image and its background. Here again, it is very difficult for an image classification algorithm, whereas a human can easily recognize and distinct a cat in this from this background or differentiate from this background. Now there is interclass variation. For example, here we can identify all this belongs to a category chair. But for a computer, the pixel values are entirely different, and it is seemingly very hard to diagnose this as all these images corresponds to single label chair. So, when we need to design an image classification algorithm, the model should be invariant to cross product of all these variations we have mentioned so far, but it should retain the sensitivity to interclass variations. So our image classification algorithm should be something like this. You have some classification algorithm and you write some magic words. And when you input your image here, the function should return the class label. So this is not much easy as like sorting some set of list of numbers. And it is not really, there is not an obvious way to hard code the algorithm to recognize a cat or some classes. For example, there are people who try to make algorithms to define a cat. Like first define the edges, and if you have some pointing edges in some direction and another pointing edges, it can be possibility of an ears. Like why is that they have tried to make some general rules. But the problem here is when you change the orientation or when you take the picture of this cat from a different orientation, all these rules get failed. Or when there is a background clutter, or when there is occlusion, this algorithm will not be working correctly. So we need to find an algorithm that is not based on a set of rules. So what next? Next is our data-driven approach. Here our idea is we feed the model with a large set of numbers with a large set of images of each category. We will download a large number of images of cat, dog, mug, hat, for example, from the net, and we will manually label all these images as cat, dog, etc. And based on those, we try to train an algorithm. And once the algorithm is correctly able to differentiate the train set, we will check it for a test set of data, whether the our trained algorithm is working correctly. So instead of a well-defined set of rules, here we are trying to learn from the data. So one important point to be noted here is, in order to make such algorithm, we need large number of data set. So there are well-defined data sets for making the algorithm. One common or one earliest type of data set is image classification data set is MNIST data set. It consists of 10 classes of numbers varying from 0 to 9, and each image is of size 28. Each of these numbers is of size 28 by 28 grayscale images. That means only single channel, and we have a total of 60,000 images, out of which 50K is meant for training and 10K for test images. And we have another type of classifier and the type of data set called cipher tag. Instead of 10 different numbers, here we have 3D images of size 32 by 32. So not 3D images, RGB images of size 32 by 32 of 10 classes like airplane, automobile. Again, 60,000 images, out of which 10K is meant for testing. Now, improved version is Cipher 10. It consists of 100 classes, and it again is again 32 by 32. Now, another biggest data set was ImageNet. It consists of 1,000 classes, and based on those, many different successful algorithms came up, and it consists of 1.3 million training images, and out of which 50,000 is for validation and 100,000 for test images. There are 50 per 50,000 50 per class is there, and the algorithm is and the performance metrics for each algorithm is measured on top 5 accuracy. That means if the algorithm is able to predict the label, the 5 labels for each image, and one of them needs to be correct. If even if the 5th label predicted by the algorithm is correct, we will take we will make that algorithm is correct. But if the 6th label is correct, it is marked as negative. So another this is 1,000 classes. There is a 22,000 classes version is there, but is not commonly used. And there is much more complex data set like MIT places consist of images from different outdoor and indoor scenes, and so these are our different type of data sets. And now let us see the machine learning. So our data-driven approach. Here we have what we do is, for making a model, first we need to collect a data set of images with the labels and use a machine learning model to train the classifier that and evaluate the classifier on the new set of images. The new set means we have divided the set into 2 parts. One is our training part and second is our test part. And during the you have 2 functions. In the training functions, we need to give our images and the corresponding labels, and after training it will return a model that is our trained model. And during the testing time, we have another function called predict function, to which we will input our trained model and the set of test images, and this model should be able to return the correct labels. Since a part of the data is divided as training and test images, the test we can know what is the actual label for the test data. So we can compare with the actual predicted label and the actual. Just a second. So let us see the first classifier. That is our nearest neighbor. Here again, the approach is like this. In the testing part, during the training part, what we do is we memorize all the data and the corresponding labels. And during the testing time, we will compare each of the test images with the memorized data. And we will check which has the least difference. And for example, let us see, we are trying to train this nearest neighbor with our CIFAR10 dataset, which consists of 10 different classes of image size 32 by 32 color images. And it will, during testing time, it find out which are the nearest neighbors in pixel-wise nearest neighbors. So we need to check which is the nearest neighbor. The process is like this. During the training time, it just memorizes all the images, that is all the trained images, and during the testing time, it will compare each of these test images with the trained image, and the image which has least difference will be, and the label of that image is taken as the label of given test image. So what we do is, for example, we have a test image like this, and this is our train image. We will take this is our L1 distance. We take the pixel wise difference, like 56 minus 10, we will get 46. Next 32 minus 20, that is 12. Likewise, we will take the difference at each location and add together, and finally we will take the sum. And similarly, we will find the difference for each of the trained images and find the point at which we have the least value here. And what we do is we will take the corresponding label of that training image, and that is given as that is outputted as the label of the test image. So this is the code like this. You have your xtrain and bytrain. Xtrain is the image and bytrain is the training label. Xtest is the your test image and test label. You are trying to load your train and test images, and using nearest neighbor, I am trying to train the images, or just copy or just memorize the images and its labels. And during the predict time, I will predict based on the test images what is the corresponding label. So this is like this. During the training time, it just copies all the images to one pointer, and during the testing time, what we do is we will compare the distance between each test image and the corresponding train image, and we will find which train image has the least distance, and that corresponding label is taken as the label of our test image. So how fast will be the, for n examples, how fast will be the training and prediction? For train, it just need to memorize. That means just copy the images. So it takes only one machine cycle. And predict time, you need, if there are n images, each test image should be compared with the each of these n images. So it takes n time cycles. So when we compare this algorithm, our training time is very much fast, but our test time is very slow. So this is not a good algorithm. We need, and the result of this algorithm is like this. We are training. This is a set of test images, and these are the trained images. And this column This column indicates the nearest neighbors picked by the algorithm when they checked pixel-wise difference. So here it is an image of a sheep, but it took an image of a bird as the nearest neighbor, or it took it gave the label of the bird as the label for the sheep. But this one is correctly predicted. So for dog, anything white, blobby kind of thing is taken as the nearest neighbor. In the case of frog, some dog is taken because it might have seen some matching with the brown colored thing here. In some cases, the algorithm performed correctly. In other cases, it is not correct. So there are different options you can take in order to find the least distance. You can take the Manhattan distance, that is just pixel-wise difference between the test and train images, or you can take the Euclidean distance. So now this which of the now another set of this are called hyperparameters. The hyperparameters means one is whether should I take one single neighbor which has least distance, or should I take the mean of three nearest neighbors and take the most repeating neighbor. So one important point is this key. How many neighbors should I take? Whether okay it should be 1 or 3 or 5 or 7 extra. And what is the distance value should I take? Should I take L1 distance, or should I take L2 distance, or some other distance? So these values depends on the different type of data set you are using. For some data set, L1 will be correctly, L1 will be have high performance. In some other cases, K is equal to 3 has high performance. In some other, for some other data sets, K equal to 1 has high performance. So these are hyperparameters. This is these values k, distance, etc. We call the name hyperparameter, and this is the choices we need to make for a particular algorithm. And these choices are we set rather than learn. We will set for we try each different choices and find out which is the best one and take the best one. So next, this is very much problem dependent, how to select those hyperparameters. And this is very much problem dependent. We need to find out which of this hyperparameter combination works best for a particular data set and takes the corresponding one. Now, for setting these hyperparameters, there are different methods. You can select the entire data and choose which hyperparameter works better. But the problem here is you are taking the entire data set. So you will have a correct match with the correct data set. If you're taking the image of a dog, it will have the correct, you're not splitting your data into train and test. So the complete train set has your test set also. So it will have highest matching, or it will have least distance with the correct image, with the same image. So this is not a good one. Next is divide the data into two part, train and test, and make your choice on your test data. But the problem here is your data will work perfectly on your test set, but when a new set of data and similar kind of images is given, your algorithm work will not perform as good as earlier case. Now there is another method. You can divide into three parts: train, validation, and test, and choose your hyperparameters based on your validation test and find out the best hyperparameters, and finally check it on the test data to check how good is your model. So this is usually followed pattern. And another best method is cross validation. Here, instead of a fixed set of validation set, we are rotating. We are dividing the whole set instead of five-fold. Here we have five-fold cross validation. Fold 1, fold 2, fold 3, and fold 4 is our training set, and fold 5 is our validation set. We will first fix our hyperparameters based on this fold 5, and we'll calculate which are the best set of hyperparameters. And in the next cycle, we will choose fold 4 as our validation set and find out best parameters. Likewise, we will rotate each fold choice for our validation test, and we will average out during the tests. Now, coming to image classification using deep learning. So now there is another set of algorithm that we call as a linear classification. And here we have two approaches. We first define a score function that maps our raw data to a set of class scores. And secondly, we have a loss function that quantifies how much good is our classifier, or how much good is our that we will check how much good is our classifier, or that quantifies the agreement between the predicted score and our actual score. And finally, we make this an optimization problem. We want to make sure that our loss or our error should be minimum, and we will make sure during the training process this error is minimum, and at the point at which your error is optimum, that value is taken as the weights for the function. So this linear classifiers can be considered as a building of a neural network. You stack any number of linear classifiers. In between, we have some nonlinear function, nonlinear activation functions, and you can build any large neural network based on with this linear set of classifiers. So the approach is directly straightforward. Here we will give or input an image to the function where it multiplies with a set of weights and it produces a set of scores. For example, if I'm taking a cipher 10, how many classes are there? There are 10 classes. For each image, I will have a score corresponding to each of the 10 classes. And for this image, I should have a high score corresponding to the cat class, and I have a low score for all other categories. So you have another parameter called weights. Here what we do is we first convert our image. This is a 3 RGB image. 32 by 32 image is first converted to single linear vector, and that means that when you multiply this 32 by 32 into 3, your size vector will be 3072 by 1 length vector, and that is multiplied by a weight vector to produce a set of 10 class scores. So what should be my weight size? You have your image size of 3072 by 1, and your output size should be, you have only 10 classes, so it will be 10 by 1 is your output size. So your weight size should be this 3072, that is 10 by 3072. So you will get, in order to have some bias, we are adding one more term called bias term, which also will have the same size as this one since addition. So it will be 10 by 1. So let us see how this happens. Let us assume an image is just having 4 pixels, and we are trying to classify only 3 classes: cat, dog, and sheep. So first, we need to stretch this pixel into a set of columns and multiply with a weight vector. We are setting some random weights, and these are the values. So 4 classes means 3 classes, and your image pixel size is 4 pixels. So it will be 3 by 4. Sorry, 4 by 3. You have 3 rows and 4 columns, so it is 3 by 4. And you have by sizes 3. So when you in order to check whether what is the score for each class, let us assume the first category corresponds to cat, second dog, and third one sheep. What we do is we multiply this weight with the corresponding image. 0.2 multiplied by 56 minus 0.5 multiplied by this one multiplied by this one, and added with this factor, you will get a score of minus 96.8. Similarly, this vector multiplied by this vector plus adding this one, you will get those 4. And this one multiplied by this, by adding this, you will get 61.95. So by looking this, we can see that this input image is classified as a dog score. Dog. Because the highest score is for dog. Other one has least score. So that's our classifier is not correct. That means we have to propagate an error backwards. That means so that whatever weight we have chosen is not correct. That's why we are getting a low score for cat and a high score for a dog. Or in other words, we can see that instead of stretching this image, we can multiply. We can form or we can take each of these rows and have a similar size of that image. So when you take the inner product of these two, we will get this one. So each of these row can be considered as a template of, here this is a cat template, this is a dog template, and this is a template of sheep score. So when you add with this bias, you will get the corresponding score. So when will be the score will be maximum? When the chosen weight is same as your input image. In that case, or when the inner product is maximum, when the chosen template and our image is nearly same or equal, we will have a high score. So during the training process, what we are trying to do is, we are trying to adjust the weight so that for each image, the corresponding template will have maximum similarity with the input image. So once it is trained, let's assume what we have is each of this template will have some matching template of the corresponding class. For example, most of the airplanes contain some blue are in sky, so it contains mostly the blue color structure. And here the car is much more easier. Like most of the cars are pink in color. It has some blobby kind of thing. And when you multiply an image with this blobby kind of car template, it will have maximum score only for the car images, and for all other images the score will be less. So this template is achieved during the adjustment of weights during the training process. Or we can also interpret this linear classifier that Wx plus p is just trying to make a plane, a hyperplane, above which the score is categorized as a car. Here it is classified as a deer. That means here we are trying to make a hyperplane that distinguish a corresponding image from, or a corresponding category from another set of categories. A given category from another set of categories. Now we have so far defined the score function. Now we need to know how good is our classifier. So from this, a human can identify this here. The cat score is 2.9. It is not correct, and it is incorrectly classified. Highest score is 8.02. That is a dog. So this is classification is not correct. But this measurement should be done by a computer. For that, we have another function called loss function. And this loss function, the definition is, or the loss function, the function is to quantify how good is our classifier. So here we have a set of input images and corresponding labels, and for each input image and the corresponding weight, we will compare with the we will compare our predicted label with the actual label and find what is the loss in each term and average us out for a set of categories. Here there are only 3 categories, so we will here average is 3. Here the difference is the whole 10 classes in order to make simplify. In order to simplify, we are considering only 3 classes. Now, there is one kind of loss function that is called multi-class SVM loss. Now, the loss function is 0 when the score of our correct class is 1 greater than the score of all incorrect classes. Otherwise, it is the score of the difference between the correct class and incorrect class plus 1. So here we just need to take maximum value of 0 or Sj minus score of the correct class minus score of the correct class minus score of the incorrect class plus 1. So let us see, and we need to take the average out. So we have provided a margin of 1. This is the score of the correct class. As initially, when the score of the incorrect class is less, our loss is high. As we move, as the score of the correct class is greater than the score of the all of the incorrect classes, our loss is 0. So this multi-class SVM loss is also called hinge loss. Now let us see how to calculate this. Now, but here the score is CAT score is 3.2, CAR score is 5.1, 1.7. Now, calculate the losses. We need to check the score of the correct class with score of the incorrect class. So, we need to take max of 0, 5.1 minus 3.2 plus 1. Similarly, max of 0 and minus 1.7 minus 3.2 plus 1. So, this is max of 0 or 2.9, or this is max of 0 or minus 3.9. So this value, maximum value is 2.9 and this maximum value is 0. So the total loss is 2.9. Similarly, find the loss for 8 cases. Here the score of car class is high. So this classification is correct. So here we found that the score of the car class is 1 greater than the score of all incorrect classes. So the loss here is 0. But here again, frog is incorrectly classified as car. So the loss is 12.9. Now we need to take the average of all this. There are 3 classes. We will take the average of all those three, and our average loss during this particular iteration is 5.27. Now, and now here, what is the minimum and maximum loss? Minimum loss is 0 and maximum loss can be infinity. So now one question is, we have found some particular value of W. Is that value in such a way that our loss is 0? Is that value of W is unique? It is not so. For example, the value of 2 times W also has loss is 0. For example, here, instead of 1.3, 4.9, I take twice the values of W here. So it will be 2.6 minus 9.8 plus 1. Here again, when I take 9.8, it is greater than all these two values. When it will be 4 here, it will be 2.6 here, but still 9 is greater than 2 of these values. Our output is 0, or our loss is 0. So even if I take 2 times W, loss is 0. So which question comes here? Which W should I take? Whether W, 2W or 4W, etc. So next is how to find the best W. I think, shall we take a break?
Yes, ma'am.
Okay.
5 minutes break.
Okay.
All stay here itself, but we can take a break. That will be enough. Please don't leave the meeting.
Hello all. Now we will restart the session after the break. I welcome Dr. Linu Shine ma'am to take over the session.
No, am I audible?
Yes, ma'am.
Okay. Shall we continue? So,
Yeah,
how
ma'am,
do
you can.
okay? Thank you. Uh, Now, next is how do you find the best value of W? That is our next task. We have made a classifier with a score function and with just a linear classifier that we just need to multiply a weight with our input and it will produce a set of score function. And we have some other function called loss function which quantifies whether our classifier or linear classifier is good or bad. Next, we need to find, we need to adjust the value of W or we need to find which is the best W. For that, we have the loss function. The loss function should be minimum. And for that, we have something called optimization. For, and our aim of optimization is we will input our loss function for a particular value of W and find out for which value of W our loss is minimum. So this optimization problem we can view as a blind man standing on some mountain height and he want to travel down toward the valley. So each point on this graph is correspond to a loss for a particular weight. And the valley point is the point at which our loss is minimum. And the height is proportional to the loss. And we need to find which combinations of W our loss is minimum or this height is minimum. So one method is you can randomly put some values and check whether the value W chosen is correct, loss has low loss. And second method is by this image, you can the blind man can feel the height by his feet and move his feet in the downward direction. So finally, or eventually, he will settle at the bottom of the valley. So first is you need to find the slope. One method is in a one dimension, you need to find the derivative and it gives the maximum value. And if you take the steepest or if you take the negative of that, it will give the steepest direction of slope. So you have your function f of x, you will just increase the value of x or weight plus some value of h and find the gradient. And when you find the dot product of your gradient in any direction, that will give the steepest descent. That will give the maximum value, and the direction of steepest descent is this negative of the gradient. So how will you calculate this? For example, let us assume the current setting of W is like this, and let us for this setting of W, let the loss function be this thing. And in the next iteration, we will change some one value of W by some small, by adding a small update and find out what is the loss and then take the gradient loss for this value. For example, I'm updating by a factor in first dimension by this value, and then I will calculate my loss, and then in order to find the gradient, I will subtract these two terms and divide by this factor. So that is my gradient in this direction. Similarly, update each parameter, calculate the loss. And calculate the loss and calculate the gradient. So this is much time consuming job and it has take too much of man hours or too much of compute hours. So this is the method of finding slope or method of finding gradients, loss with respect to gradient as a by using this numeric gradient is tedious. So instead of this, we have something called analytic gradient, which is a fast method. For this, what we do is we will take the partial derivative in each direction. So the whole stage consists of two parts. One is the forward path and second is backward path. And do your update of your neural networks is done during the backward propagation. And that means during the backward propagation, you will update the values of weights and you will find the gradient and find which values, what all necessary update should be taken. So let us assume a simple example like this is the, for this thing, we first need to draw a computation graph. So a computational graph is just, so in the previous case, this is the computational graph of a function. We have our weight matrix, we have our input function, and this is passed to a loss function or score function, and we will get some loss function by using this, and we had some regularization loss to adjust to check whether it's overfitting, and we will come. How do we calculate the loss? By comparing our predicted value with our original value. So similarly, for every function, whatever function we are writing, we need to draw a computational graph, and based on this computational graph, we need to find the gradient at each node. So let us, you have your function is, let's assume the function or your score function is like this, x plus y into z. Then, and the x, y, and z values are here. Then you just need to draw the computational graph. So x plus y, you have plus node. Then multiplied by y, you have a multiplication node. Here, I am giving an intermediate node named q, and my final function is f here. So during the forward pass, my multiplication value minus 2 plus 5 is 3, minus 4 into 3 is minus 12. And here, when I take the derivative with respect to f, dou f by dou f is 1, then I need to find dou f by, I need to find the derivative with respect to q, dou f by dou q. Then dou f by dou q, f is, we know it is q is z, dou f by dou q is z, and similarly dou f by dou z is q. So this value dou f by dou q is z. What is z value? Minus 4. So this value will be minus 4. And next value is dou. We need to find what is dou f by dou y. We directly does not have any relationship between this f and y, but we can apply the chain rule. Dou f by dou y, we can write it as dou f by dou q into dou q by dou y. So this dou f by dou q, this is your upstream gradient. The gradient need to come from this part, and this is your local gradient, dou q by dou y. So what is dou f by dou q? Dou f by dou q, that is z, and dou q by dou y is equal to 1. So your value will be dou f by dou q is minus 4, and your upstream gradient is minus 4, your local gradient is 1, 1 into minus 4, minus 4. Similarly, you need to find what is dou f by dou x, that is again minus 4. Like for every point, you need to calculate what is the thing. Now, once you have found out the gradients, the next step is you have the optimization algorithm. One of the simplest algorithm is gradient descent. Here what we do is we iteratively step in the direction of the negative gradient, and we continue this process until for a finite number of steps until which our losses minimum. So the function can be written like this, or it is a vanilla gradient descent. We first initialize the weights, and for some time steps we will first compute the gradient using the function we have mentioned so far. To this function, we need to input the loss function, uh, the corresponding input data, and W, and it will calculate the gradients. And we need to update our weight in the negative direction. So we will take a factor of this gradient or weight, and that is updated with the current weight. So here are the parameters. We don't know how many times we need to iterate. So that is hyperparameter. First one, weight initialization. So depending upon the weight, you cannot choose any random weights. Based on this, your output may be completely disastrous, or there are proper guidelines to take the. You can have some weight initialization like saver initialization. You cannot make all zeros. So based on your data set, you need to find out which type of initialization should be done for your weights. And the next is how many times I need to iterate, and what should be the learning rate. Should I take a larger step, or should I take a smaller steps? So these all are hyperparameters, and these are to be set rather than learned. So when this is, let us assume we have only two set of weights, W1 and W2, and this shows a heat map, and this white point is the point at which we are moving in the direction of negative gradient, and this red region corresponds to the point at which our losses minimum. So for each step, we move in the negative direction, at finally we will reach at the local minimum, at the minimum. So this path is not exactly a linear path. So it will something like similar to a taco shell. So we will have a path like this. First it increase, and just first it decrease. The path taken will be like this. It take a curving like path to reach the final point. And there is another variant called stochastic gradient descent. The advantage here is for every update, we need to, for example, here we need to, in order to find the loss, I need to calculate the loss from each of the data set. If there are 10 million data, for each data set, I need to calculate the loss. Then only I can find out the average loss. So this is when the data set is when the data set is too large, or your training data set is too large, that this is very time consuming. For every update, you need to take millions of seconds to identify the loss. So one major step is you divide the data into a number of small batches or mini batch, and you take the loss for each mini batch and make the update. So here, your hyperparameter is you need to find out what should be the batch size. How many number of pictures should I? How many number of images should I take in a one? Whether 32 number of images, 64 or 120, or how should I sample the data? Whether should I take random samples or fixed number of samples? So, so there are different kind of optimization algorithm, and these are the earlier type of stochastic gradient descent, and are the earliest type of optimization algorithms. Now, most commonly or most popular algorithms are called ADAM that we are not discussing today. So, during your training or during your actual training process, you can use ADAM, RMS prop, etc. That has much more converging than yours gradient descent algorithm. Now you can add. We have said earlier we have our linear function, and we can add any number of layers. We can stack our linear classifiers to make a big network. So this is something like this. You have your first linear network W times X, and your final function output is f into W2 into max of 0, comma W1x. So you have an input. Your input is 3072. Oh, dimensional input vector. You have another W1. It produces intermediate node. See, now the size is reduced to 100. Finally, your end output is you need to have 10 classes. So you're from 100 to, you have reduced to 10. Now the question is, why you are using a max function here? Why you can, sorry, similarly you can stack a 3-layer that we will take W3 max of this term, 0, comma W2 max of 0, comma W1x. Now how so for a 2-layer network, what here we do is for every element, every 372 inputs has a connection with every 100 layers. So it is highly interconnected, and each of this multiplied by a weight matrix W1, and similarly each one is connected with 10 output neurons. Hidden layer, each of the 100 hidden neurons is connected with the 10 output neurons, and this is again another highly dense system. So this we call a fully connected network, something like this. And this we call the name a multi-layer perceptron. Now the question is, why this max of function is here? Can I take just W2 into W1 and of x? So when you take like that, it is just W2 into W1 of x. That means it is just W2 and W1 can replace by another big matrix W3. So it is again linear function. So if you're, that means we cannot interconnect two networks. We are just making only a single linear score function. So in order to interconnect a network, we should have some activation function, and here the activation function is called, or this is a non-linearity introduced by max function. Here we need to take the value of 0, or if the value is negative, we need to take 0, else we take the whatever there is positive value here. So this introduces non-linearity between layers, and this non-linearity is introduced by the term activation function, and this is example of ReLU activation, rectified linear unit. And now what's the difference? In the previous case, in the linear function, we have a single template per classifier. Now, if I have 100 layers, hidden layers, I have 100 different templates. So, for example, here there's a horse. In the previous case, we have two horses. One is left-facing horse and right-facing horse. But in a single linear classifier, the template formed was two horses, one east-facing and other west-facing. But such a horse is not seen in actual life. So here we have the horses, 10 different horses are there. There are 8 different horses, 8 different templates, and each one have horses. Some of them have horses looking in one direction, and another one looking in the opposite direction. So it now the system is having much more templates and much more matching informations. So here the input, again we are having input matching, and if either one of this input is matching, we will have a high score that is again mapped to our output. So that is shown here, left facing horse and right facing. So we can say that our first layer is a bank of templates, and our second layer or our hidden layer is a bank of templates, and the final layer combines all these things. And here you can add any number of layers. For example, here this is 6-layer architecture. Our input is X and output is S. And between all these things, you have to add between each fully connected network, we need to add a nonlinear function. So we have discussed the non-linearity is introduced by activation function. There are different type of activation function, and this is called linear activation function. When the value is negative, your output is 0, and the next neuron is triggered only when it is positive or 0, or greater than 0. So there are different type of activation function. You can have sigmoid activation function, tanh activation function, Relu's equation. This varies between -1 and +1. You can see here the range of linearity is only very limited, but here is highly linear here. Here we have a saturation. So that is avoided here. That is again avoided here. There is another combination called maximum. So these are different type of activation function you can use between your layers. Now the general structure. Coming to, so far we have discussed only the fully connected network, how it is classified into one of the 10 categories. In the case of a CIFAR 10 dataset. Now you have your image, and in the case of an image, when it's converted into a single layer, some of the information, some of the spatial information get lost. So here we need something called convolution function. So here you have an image, it is first passed by a set of convolution layers, and between each set of convolution layers, we will have ReLU, and at some, it is ReLU is an activation function. We have discussed that is max of 0, ReLU. Then you have pool functions, then interpost again convolution, ReLU, convolution, ReLU, another pool, etc. Finally, after getting all these informations, finally it is converted into a single layer, as we have done for a fully connected network. That is, it is converted into a single column vector. Then it is given to a fully connected network where it gets classified into any one of the 10 classes in the case of CIFAR 10. So now let us see how this convolution neural network happens. So here, in the previous one, we have only one single matrix W for each neural network layer. Here again, we have a space. Instead of that, we have a two-dimensional filter, and the values of this filter weights get updated during the training. So let us see. Let us have a much more closer look. We have our same CIFAR 10 dataset whose image size is 3 by 32 by 32. Here we apply filter, and what we do is we randomly fix some values based upon the weight initialization, and we multiply each term of the, we will place our filter on the image, and cross multiply with each term on the filter with the corresponding term on which is overlapped on the corresponding term on the image, and this multiplication is done depth wise, and it will produce one term corresponding to whole multiplication, that is 5 by 5 by 3, that is total 75 plus 1 bias term. After this much of multiplication will result to one single neuron. So when you try to place over this whole thing, when you slide this filter over the whole filter map, your or over the whole image, your size, your convolution size, your output will be a sheet of neuron of depth 1 or size depth 1 and height and width of 28 by 28. Now let us see how it has happened. For simplicity, we are not now discussing three-dimensional depth. We just have a two-dimensional depth. If it is three-dimensional, in the case of channel depth 3, assume the filter has, we are taking the multiplication at each depth and added together to form a single product. So here I have a 7 by 7 image and a filter of 3 by 3. So what I do, I will place my filter here such that and take the cross product. So we will take the cross product at the filter point and the corresponding location on the image, corresponding pixel point, and take a weighted sum here and add with bias. So how many times, then move each column, move by each column. So that means stride is 1. So how many times you can move? 1, 2, 3, 4, 5. So your output size will be 5 by 5. Now, if I'm leaving two columns, 1, 2, 3. So my output size is 3 by 3. So depending upon your stride, your output get reduced. Now, if my stride is 3 by 3, if stride is 3, I'm leaving 3 columns because it will not fit. Next point, it will be here. Next point, it cannot be used. So what is general formula to find the output? You can have an equation like this. N is the total image size or your convolution size minus F is the filter size divided by stride plus 1. So N equal to 7. N equal to 7 means your filter size is 3, 7 minus 3. Stride is 1 plus 1 divided by 1 plus 1. That is 7 minus 3, 4 plus 1, 5. That we have found out. Similarly, stride is 2, 7 minus 3, 4, 4 by 2 is 2, 2 plus 1, 3. So this is not possible. Now, the problem with the previous case is your output size and the input size is different. If I want to retain my size, we have earlier said that why we went for this convolution network type of network is we want to preserve the spatial dimension. If I want to read more and more information, using the filters, we are extracting some information from the image. If I want to preserve that spatial dimension, we need to have the exact dimension of the input image. I need to have zero padding. So if if my pad is 1, what I do is I'm padding all the edges with with zeros. One zeros on all edges. So I can move 1, 2, 3, 4, 5, 6, 7. So 1, next time 2, 3, 4, 5, 6, 7. Then the time you can move. So in this case, my output size will be 7 by 7. So in general, if my filter size is 3, I need to pad by 1. If my filter size is 5, I need to pad by 2. And filter size 7, I need to pad by 3. So this is once again. If I have 5 by 5, 3, if my filter depth is 5 by 5, because here input depth is 3, my filter size should be 3. There are such 6 filters are there, then my output size is a 28 by 28 dimension. Since there are 6 filters here, uh, each filter will produce an activation map of 1 by 28 by 28. If there are 6 filters, it will produce 628 by 28. So depth of the activation map is 6 by 28 by 28. Next, I need to take, if my filter size is 5 by 5, I should have a depth of 5, 6. And if there are 10 filters, output will be 10. When I take 28 by 28, when I substitute the formula, I will get the size will be 24 by 24. So if this process continues, first 32, then 28, then 24. That means shrink is we are reducing the sizes very fast. So one method is you can pad with zeros. So if my pad is 2, my filter size is 5, then I can my equation should be our image size 32 plus pad is 2, so 2 times pad minus filter size by stride 1. So output is same, 32 by 32. Now how many parameters? Parameters means how many, what is the output size? 10 by 32 by 30. The output volume size is, if there are 10 filters, there will be 10, 32 by 32. Since stride is 1 and pad is 2, the output dimensions are preserved. Then number of learnable parameters. Learnable parameters means that during the training, the weights, values of filters get changed. Finally, once the training is finished, the values get permanent. So all the values at the filter points are learning parameters. So how many such points are there? If there are 3 5 by 5 filters, this 5 by 5 filters need to move towards the depth. So 3 by 5 by 5. That is the total number of operation multiplications plus 1, that is 76. If there are 10 such filters, 760 learnable parameters are there. So these are some hacks. Outputs you can use. Now, so we can use, we can add any number of any set number of convolution layers to extract the features. So the initial set of convolution layers will be learning the lower level features, and the higher level convolution will be learning the mid level features. And as we move up, it will be learning the higher level features like distinction between the nose and ears, etc. in the case of an image. Now, if you want to reduce the size, if I want to reduce 64, if there are 64 is the input, the depth and dimensionality, but I want to preserve the dimension, I can use one by one convolution filters. If there if you need 32 one by one convolution filters, I will get my output map will be output depth will be 32 by 56 by 56. So we have said earlier, when we take the product on a one particular point, we will get only a single number, and this single number can consider as a neuron. So we have such 32, sorry, 5 into 5 into 3 plus bias. So that's our weighted sum here. And this is then passed through an activation function to produce the activation map. So this each when you add any number, if there are 5 filters, each of these 5, if we look at one particular point, each of these 5 filters will have different weight, and it is looking at the different. It is extracting different features from the network. But to convolution, now next is this we have set earlier. The first in the case of fully connected network, each we have said that it tries to learn 10 different templates of the same images, right? But here the difference is, here an image is divided into smaller sections, and trying to learn some information, maybe some edges, some oriented edges, or some opposing colors, by is learned at each template of this filter. Now there is left is our, we have discussed ReLU, next is pooling layer. So we have discussed whether we can extract the information without reducing the size by zero padding, or we can continue reducing by using without any zero padding. So if I want to reduce my dimension at some point of time, I can use a pool layer. So one method is max pool layer. So in pool layer, if I am using a pool layer, I can directly reduce 224 by 224 by 64 can be halved. 112 by 212 by 64. So it is equivalent to downsampling. So what does a pool layer do? If my pool, if I have a filter size of 2 by 2 and my input dimension is 4 by 4, I will place my filter here. This is max pooling. I will extract which is the maximum value here. Here the maximum value is 6. Next, I will slide by 2, move the filter by 2 or stride 2. Then my position will be here. And what's the maximum value? 8. Likewise, at each stride position, I will extract what is the maximum value here, and that is my output. So by doing this, I'm trying to reduce my size. So this is the general formula. It's if your input size is this one, and it produces an output volume like this, whose dimension will be W1 minus F by S, and H2 will be this one. And remainder is the fully connected network that we have. Once our image is finally, whatever the information that is gathered after this set of fully connected, convolution layers and fully connected convolution layers and pool layers, finally at that point, we will stretch into a single column vector and give it to a set of fully connected layers. Can be a single layer or a set of a set of a number. It can be a set of hidden layers, including the hidden layers. So here, if the input is 3072, it will be first converted into, or weight matrix will be 10 by 3072, and output volume will be 1 by 10. Now, next is there is an important data set, namely ImageNet provided by this ImageNet large scale visual recognition challenge. And each year there was several winning algorithms. And this start for 2010. Sorry, in 2012, the AlexNet was the first neural network which won by a margin more than 10 from the previous year. And each year, the challenge winners, the error margin got reduced drastically. In 2015, the error rate is 3.57. It is a 152 layer architecture. That error rate is around 3.57, and the error rate by a human is 5%. That means the error rate is now for this particular challenge, it is much less than a human. So one important point we have mentioned is deep learning requires a large number of training data and large compute power. So you can minimize this. We can completely remove. You can reduce this requirement provided you are training that there is some similarity between the training your data set and the existing data set of well-known data set. In that case, you can use a train network and retrain some part of it. So, for example, you have a large, but you have a network first trained on ImageNet dataset that consists of 1.4 million. So, what we do, if you have a small number of classes, say C classes, what we do is we remove this final layer, fully connected layer. We assume that these C classes are a subset or have a similarity with our ImageNet dataset. In that case, what we do is we freeze all these layers of a trained neural network that is trained on the ImageNet dataset, and we will reinitialize the final layer. In the case of in the previous case, there were 1,000 classes. That is why this fully connected layer has output of 1,000 neurons. Here we have fully C classes are there. Our output consists of fully C class neurons here. So then freeze this much and retrain on the other set of images of C classes. And after training, this network will be able to differentiate different, should be able to work well for your data set. And if you have a bigger data set, similar to our master data set, image net data set, then you can unfreeze a large amount of higher layers and freeze the remaining layers and retain the data set to get a good result. So always remember, do not start from scratch for your, or do not start from scratch for your data. You can use any network that is trained on similar kind of data. So the logic is similar. If you have very little data and you have your data set is very similar with a well-known data set, use a linear classifier on the top layer. You just need to unfreeze the top layer and just rearrange the linear final classifier. Now you have completely different data. Next is you have a large amount of data set and you have a very similar data, and your data set is very similar to the well-known data set. Then again, take the trained network on the larger data set and you can fine tune much more layers. Now, if you have very little data but your data set is entirely different from the common data set, then you are in trouble. You have to use linear classifier from different stages. You have to retrain. Sometimes you will get a good result, sometimes it will be bad. And the next condition is you have quite amount of data, but it is difficult. But here again, you try retraining from the do not start from scratch. You unfreeze the top set of layers and start training. Why we are saying so is in every network, however large or small, the initial layers will be always same. Even if in RustNet, GoogleNet, BGGNet, etc. First few set of convolution layers always look at the same set of information. It will be looking for the low level features like edges. It may be looking for opposing colors, or it is looking for some kind of blobby structures, etc. So this is common for every network. So no need to retrain for your particular network. So you can use any well-proven network. You can unfreeze only. You need to unfreeze only the top layers and train for your data set. Now, coming to uses, it can be used in medical imaging and to identify any malignancy like tumors, cancers, etc. And in face recognition, you can unlock your mobile phone by using by looking into the mobile phones, and you can by using biometric scanners. You can verify your Aadhaar, or you can bioration, etc. And there are furthermore importance like object identifications in satellites, and there is augmented reality, gaming, and furthermore security can be added by using iris recognition, both in mobile phones and bank wallets, etc. This can be used. And right now you can use this Google Maps to find out the nearest good restaurants, or it will give the interactive maps, etc. Now, this image classification is a building block for many other tasks. For example, object detection. Here, in object detection, the difference is in an image classification, what we are doing is we are trying to label an image, or we are assigning a label to a 2D image. The difference in object detection is we try to draw a bounding box for every object in an image and give the name, give the corresponding label of that object. So here there are two objects, one is a person, another is horse. So here we need to draw a bounding box, name is as person, another bounding box horse, and label it as horse. And you can also like so one method is trivial method. This is not actually used here. In early days, what we do is we will move certain different we move different sliding windows and try classification jobs. So this is the background. Then we move the window further. Then we capture the person. So this is captured as person. Likewise, different windows are taken, etc. Now another example is image captioning. Here we first give an input and give a start word like riding, or first maybe a man. We will give the first start word maybe start, and from this they have identified what is the person here, main object here, that's the man. Then it will when the man is the input to another network called RNN, it will derive the next word called riding. After the next when riding is there, the next word will be automatically detected by the RNN as a host. So this image caption is another uh, building another application for our image classification. So that's all with our theory part. Thank you. Any
Now
questions?
we will now we will have an interactive section. If the participants have any queries, they can come up. You can mention your doubts in the comment section.
ഹലോ എടാ ഞാൻ ക്ലാസ്സിലാണ് കുറച്ച് കഴിയുമ്പോൾ വിളിച്ചാൽ മതിയോ ശരി ശരി ഞാൻ വിടാം നോക്കുന്നുണ്ട്
Hello.
Hello.
Hello. Good evening, Dr. Linu. And
Good
it was a
evening.
very wonderful speech from your speech on deep learning. I just wanted to ask you a few things.
Okay.
Firstly, when we think of neural network, nowadays, first what comes to your mind is about the CNN, convolutional neural network.
Okay.
Right. So, what is the big advantage by which everyone is focusing on this convolutional neural network?
Okay. Thanks for the question. And um, mostly convolutional neural networks is mostly used for this image type of applications. One big advantage here is conventional machine learning system. You need to identify the features from the image by a human. Maybe
Yes.
if you're trying to. So that is whatever the features identified this human. Sometimes it will be correct or correctly matched, or
Yeah.
sometimes it does not. The features identified by these humans are not sufficient for the correct classification. Now, the advantage here in the case of a convolutional neural networks, the network can automatically extract the correct features to identify for a particular task. So that means it is much more easier compared to any common any machine learning algorithm or a general rule of structures or any common general general programming. So that is why people are falling for this CNN networks.
Okay, ma'am. And is there any other more efficient method than this CNN?
Once if your data set, if you're correctly able to identify the correct set of features, whatever the machine learning is much better than CNN. But the
Okay.
problem here, because it has much less compute power required. But in the case of CNN, you require much large amount of compute powers, and sometimes you need to wait for some few days or few weeks to get the result. So that much of man hours will get wasted, and that much of resources will get wasted to identify the correct features. Sometimes these features extracted by this network may not be the correct one. By some accident or something, you are getting the result.
Okay. So you mean to tell that before you proceed, we need to have a good literature review, as well as we need to understand our project better, right? So that it's
Yes,
all application oriented,
yes,
right?
that is very much important. If you first have to check whether the same application can be done by using any conventional methods, and if you're getting good result, it is better to go for that.
Yeah, and
And
many of the algorithms that you have told are all application dependent, right?
yeah,
All right. Okay, ma'am. Thank you.
okay. 1 minute we can have. I will just share my. a hands-on session on this image classification. Are you able to see a link shared
Yes,
in the
ma'am.
comment box?
Yes, ma'am.
Okay, you can click on that link and you will get a collab file. So I'm sharing my screen here. So this is how it looked like. And once you get this, you have to use this save a copy in your drive. Take some time. Are you able to open? So you will get a name like this, copy of FTP flower classification training .ipython notebook. Have you got like this?
Yes.
So you can, once you that copy is created, you can give your own name. Whatever your name that is you like. And then you have to select from the runtime, select change runtime type and select the hardware accelerator GPU. So this is a tutorial to classify different type of flowers from the images. So I hope all of you are familiar with IPython files, or are there any new members? So you can here, on the top of this top left corner, you can see two options. One is plus code. Here, whatever you write, you can write any code by pressing this button and say some y equal to f of x. Any code can be written like this using this plus button, and if you want to write any comment, you have to select the text button, and this is my first program like this. So whatever written here will appear as text, and other times it will be appear as code. So here what we're trying to do is we are trying to understand data, and we are trying to create a model to identify different or differentiate or classify different type of flowers. So first part is we need a set of libraries, like to plot the or to view to visualize the images. You need matplot. To do some mathematical operations, you need numpy. You need some OS based operations, some image based operations, so you need pill library, another TensorFlow library to convert the tensors, and the libraries keras, so you can add we have seen that for a for classifying, we need a set of convolution layers, max pool layers, some activation functions. We have libraries, all these functions are written in this built-in libraries, and we just need to code this libraries. And so first part is we need to execute, or we need to call this libraries, so that we need to execute the cell. For that, we need to just click this part. So it shows that it's executing. So first, it is connecting to the server, and a set of RAM and disk is allocated for our process. And there are, in this tutorial, there are around 3,700 flowers, each category of daisy, dandelion, rose, sunflower, and tulips. So it comes under the folder flower photo. So this data set is provided by Google API at this location as a tar image. So I'm going to import that using this command, import pathlib, and I'm giving the path to import that images. So when I execute this, that images get downloaded and get filled to this disk, this location, data directory. So after this, we are trying to see what is the image, how many number of images are there. We are trying to, so just 3670 images are there. We are trying to print the image count. So that we are using the len function and trying to print all the .jpg files. Now here we are changing. I'm trying to view what is the image at the location at the 10th position. Here I'm. So this is some white rows. You can any number here. This is a this is a list. Consists of the list of roses. So all the roses get downloaded to this location, and we are trying to visualize using the spill application, spill image function. Then this is the 9th image. Now you can see any image over here. I'm opening each directory, and this is tulips again. Now we have said again to live. So we have different type of images that got loaded into our disk. Now next is we are trying to we have said instead of finding the loss function as a completely as a whole, we can train as batches. So we have defined what is the batch size and what is the size of my image. So I have defined my batch size as 32, image height and width as 180. So this is defining. And next part is dividing my data into validation and training. So I am using this function. That is a function written as Keras library that can divide the data into a validation split of 0.2. That means 80% of data. 80% of data is taken as training. Rest is our validation in the training subset. So out of which 734 file was taken for validation. Next, how many classes are exceed only on the different classes here? And what we do is we are trying to figure out the training wages. So this is different. Some of the training images, roses, dandelion, and labels. Now next, we are trying to find the labels. Now we are trying to auto tune for performance. Now that we are applying some normalization, that are some of the regularization factor. We are making the scale instead of 0 to 255, all the values now converted to 0 to 1. Each image values. So the minimum value is 0 and the maximum value is 0.9. So the normalization procedure is done. Now we are creating our own model. We are taking the number of classes. The final layer equal to the number of classes, that is the length of class. There are 5 classes here. And we are defining our own sequential layer. That is, first we have rescaled, then we have one convolution layer, one max pool layer, one convolution layer, one max pool layer. This is what we have said. In Keras library, we just need to call layers.convolution 2D. So here there are 16 such filters are there of size 3 by 3, and padding is same. That means same as the input image. Activation function is ReLU. You can make different activation function like ReLU or TANH, sigmoid, etc. But ReLU is better. Now, all these conv2D functions are called from the library Keras. So we just need to call this function value layers.conv2D. Similarly, just we do not write code for this max pooling function. Just call the max pooling 2D from the Keras layers. So here the function is first we rescale our input image, then apply a convolution operation, then a max pool, another convolution operation, max pool, convolution, max pool. Finally, we flatten into a single layer, and once two fully connected layers, that is this is the intermediate layer, finally equal to number of classes. Then, so I am compiling this model. Then optimizer Adam is used. This is my model summary. This is what we have said earlier. I'm training only for 10 epochs. After this, I'm trying to visualize the accuracy plot and loss plot. So my training accuracy and validation, I have only accuracy of 0.6. So it is not good, but loss is very high. So this is a case of overfitting. That means our data, our model learned over is works well for the training data, but fail miserably in the test case. That so there is an overfitting case. So we do some methods to eliminate that. That is data optimization. With that means we increasing the image sizes. That means same images is rotated, shifted, scaled, etc. So that the number of images is same is increased. So this is slightly rotated, or we are adding rotated left or taking the mirror image, etc. Likewise, different operation are there. There is another method called dropout, where we can disconnect some of the neural dense layers during the training process. So these are different regularization methods to reduce the overfitting. Then we are again compiling. Again, I'm training for 15 epochs. After that, I'm trying to visualize this tree. So let us see the now we can see there is less difference between the training and validation. That means we have trained our model correctly. Let us check. We are downloading one sunflower image, and let us see how it is predicted. So data is downloaded, and it just says that it says that the image is 52.72% confident the image is a sunflower. So this is the image we have downloaded. So it is a sunflower. It's more than 50% sure that the image is a sunflower image. So this is a classification method how to classify different images. Hope you are able to do this. That's all with today's class, and thank you all for listening and your patience.
Thank you, ma'am.
If you have any doubt, you can contact me by mail or anything.
Amida. Hello.
Hello.
Interaction കഴിഞ്ഞു.
I express my gratitude to all the esteemed participants of the session for their presence and contribution to make the session a great success. I extend my gratitude to our resource person, Dr. Linu Shine, ma'am, for the wonderful. Thank you, ma'am.
Thank you.
Finally, as an appreciation for Dr. Linu ma'am for the time and her valuable input she has shared to us today, I would like to offer a small virtual memento for her effort of appreciation. Thanks, ma'am. Your presence has been very valuable to us. I would like I would like to thank Linu ma'am from bottom of my heart for taking her valuable busy schedule to be an expert for our FTP. Thank you for the outstanding lecture, and your way of presentation was excellent. You have started from the very fundamentals of deep learning and slowly progressed to deep learning for image classification, so that even a beginner can easily understand the basic concepts. I think she have covered almost all important concepts used in deep learning in the last 2 hours. I thank you, ma'am, on behalf of our FTP team, all participants, and our department for your wonderful lecture. Thank you, ma'am, for your valuable presence. Okay, thank you all. We can have tomorrow session at 6:50 p.m. Thank you, ma'am. Thank you all.